we have this picture of living systems minimizing their entropy, keeping themselves ordered, and we also mentioned how this kind of necessitates the building of models to anticipate what's going to happen and respond adequately. And one of the things I find really exciting with the free energy principle is it seems to offer a way of bridging these two aspects, where on the one hand you have a real thermodynamic system, a physical system, and on the other hand you have models, information, and we use different language to talk about these two things. But there are two types of free energy. One that each seem to live on either side of this divide, but they relate to each other. So perhaps we could maybe describe what they are and then unpack how they relate to each other.
I see. Yeah, no, absolutely. So I guess what you're talking about is the distinction between the thermodynamic free energy and the variational free energy that speaks to understanding dynamics in terms of probability distributions. And you're absolutely right. They describe different things. They are formally equivalent in the way that they are constructed mathematically, but they refer to very different probability distributions. So perhaps the simplest way to understand the difference is in terms of what is a free energy. So a free energy is an interesting construct. It's if you like, it's a relative entropy that's equipped with an additional term, which is an energy term. So to be a free energy, you have to have an energy and an entropy, basically. And then you ask, well, what is an energy and what is an entropy? Now, the entropy is easy to answer. It's just the shape of a probability distribution, a probability density, which could be over continuous variables. It could be like a sort of bell-shaped distribution, or it could be over discrete, say coin tosses. It could be sort of 50-50. These are examples of probability distributions and densities, respectively. And the entropy just scores the average uncertainty in these distributions. If it was a bell-shaped distribution, a very wide dispersed distribution would have a very high entropy, a very confident, very precise belief. Sorry, I've used the word belief prematurely, and I'll explain why in a second. A very small entropy would give you a very peaked distribution. What about the energy bit? Well, it so happens that you can if you just drill down on all of physics, whether we're talking about quantum mechanics right through to classical mechanics, entropies are basically log probabilities, the logarithm of a probability, so that the probability can only be sort of between 0 and 1, say, but the logarithm can go from minus infinity to plus infinity. So the log of a probability is effectively an entropy. You may know it as a potential, for example. So both the bits that constitute a free energy are really attributes of a probability distribution. If you now condition that probability distribution on something, for example, me having a probability distribution, or my internal states, or a gas, then those become conditional probability distributions, and you can start to call them, in certain circumstances, Bayesian probability distributions or Bayesian beliefs. So now what you've got is a single number, a free energy measure of beliefs, and the question now is, well, what kind of free energy kind of free energy are we talking about? Reduces now to specifying what particular probability distributions you're talking about. So if you're talking about thermodynamics, and I should preface this by saying that the maths is identical, that the functional forms of the equations are absolutely identical, and also all the names are identical. But there's a profound difference between the kinds of probability distributions that thermodynamic free energy and all the attending thermodynamic constructs like enthalpy and energy and potential talk about, and those that are slightly more general in the sense they just apply to distributions over states. and in particular, sort of internal states and external states once you've got this Markov blanket in play. So the difference between, well, let's just take that as an example. The difference between the variation free energy that we are talking about in relation to building models of the world and inference pertains to probability distributions over external states of affairs, whereas the thermodynamic free energy would pertain to the actual distribution, say, of neuronal activity that is encoding those external states of affairs. So that fundamental difference is a difference between the probability distribution of something, say my neural activity, or a gas in some container. So I've got my neurons in my skull, or a gas in some container. The distribution of the different states of my neurons in a skull, or atoms or molecules in a container, that would be the thermodynamic entropy. And usually speaking, systems like you and me minimize that. They try and resist the second law of thermodynamics so that we don't dissolve, dissipate, decay, and all those horrible D words, including death. That's not what the variation free energy is about. The variation free energy pertains to a distribution, a belief about external states that's encoded by the internal states. And there, interestingly, you want to maximize the entropy. You want to keep your options open. You don't want to commit to a very precise belief or a very precise hypothesis or fantasy about what caused these sensations. You want to give yourself a bit of wriggle room, a bit of altitude. You still want to have quite an accurate prediction or account of the sensations and to be able to predict them. But you want to do it in a way that is as simple as possible, in accord with Occam's principle. Therefore, you're trying to minimize your free energy by maximizing the entropy. So this speaks to an easy paradox if you don't understand the distinction between the informational, the variational free energy, and the thermodynamic free energy. In minimizing the variational free energy, remembering that free energy is equal to energy minus entropy, you're maximizing the entropy, keep your beliefs as accommodating as possible. Whilst the concomitants of that from the point of view of the thermodynamic free energy of the states of the brain, for example, or your body, that are encoding, standing in for, parameterizing these beliefs about the external states, they will generally be subject to a decrease in the entropy. So that sort of opposition between the thermodynamic free energy and the informational free energy is absolutely crucial to this sort of mechanics of self-organization and sentient behavior. And as you rightly point out, the free energy that we're talking about is applied to beliefs about things. It's not the information inherent in the behavior of a gas or a bunch of neurons. It's what that particular configuration of the gas or the bunch of neurons encodes or parameterizes in terms of holding beliefs about the outside.
Right. And is it accurate to say that the process of minimizing the variational free energy is equivalent to minimizing prediction error or surprise, these errors in your models?
Yeah, under simplifying assumptions, the variational free energy just reduces to a collection of squared prediction errors in exactly the same way that, if you've ever done a t-test, for example, you're just trying to find the difference in, say, two group means from two bunches of data that minimize the residual sum of squared errors. So, the simplifying assumption is actually quite an important one. It's just that all the randomness, all the uncertainty is well behaved, in the sense that the random fluctuations conform to Gaussian probability or bell-shaped distributions. And I mention that because that's such a ubiquitous and commonplace assumption, and probably a veridical assumption, that nearly 90%, if not 99% of statistics is based upon that same assumption. That's called parametric statistics. And in that, under those parametric, normally distributed or Gaussianly distributed random fluctuations or effects, then you can always articulate the free energy as basically the squared residual errors, prediction errors, and then you can go off and talk about predictive coding, predictive processing as prediction error minimization. Technically, what I've taken to sort of iterating in more technical discussions is that you can always write down a free energy gradient as a prediction error, even without that sort of parametric assumption. Why is that technically important? Well, if you remember from the higher the physics perspective on self-organization, we're talking about flows through some abstract state space that now we've carved up, using our Markov blanket into stuff on the inside and stuff on the outside, and these flows basically are downward flows on a potential function that just is the variational free energy. So it's just like a marble rolling to the bottom of a pudding basin, finding its minima, looking as if it's aspiring to the most likely, the minimum potential, the maximum evidence, the self-evidencing optimum, which is at the bottom of the pudding bowl. But what's actually in play from this deflationary tautological account is just a potential minimizing gradient flow, which means all you need to know to either describe neuronal dynamics or indeed the kinematics of your body, or what you secrete or where you look, all you need to describe or simulate are the free energy gradients, the potential energy gradients, if you like, from the marble in a pudding bowl metaphor. So the free energy gradient prescribes, defines, and quantifies the dynamics that underwrite the self-evidencing and the inference and the predictions. Therefore, it is important to know that a free energy gradient can always be written down as a prediction error, which gives greater license to those people who want to talk about predictive coding and predictive error minimization. You can go beyond Gaussian assumptions to do this at the level of these fundamental gradient flows.